And there's also a finance, so you can do well to make up. The solutions will be uploaded. Is it uploaded? Can you do that right now? Okay, the solution will be uploaded. Okay, so we were looking at regression and we looked at this algorithm called OLS. We tried to minimize the residual sum square. And it led to an explicit form. Oh, stop. And we try to understand what this equation meant. Okay? So I hope everyone sort of have a good feeling for what have a good feeling for this equation. And then I sort of went on and told you about the problems associated with OLS, okay? And then suggested a way to correct for that, okay? And the solution was given here, W. And I also went on to say what this solution was trying to minimize. And this was what it was trying to minimize. Okay? It was minimizing the residual sum and also minimizing the weighted square. Okay? And you take the difference, you take the derivative with respect to W and set it equal to 0, and you will get that. Then I went on, this is where I stopped. I had a general formulation where I'm minimizing the residual sum, or sum squared, represented by this thing right here. This part is the residual sum squared. Okay. And this can be represented in a matrix form. And then I have this extra thing, which I call the regularizer. And this was sort of a general form, more general than the ridge regression that we were doing. So if I had to write this in terms of elements, so let's say if W was Y, W then this will be I 1 through P and W I squared. Or I could write this thing as And here I have a sort of a general form. Okay. Where a general form. So, and essentially you could do this. Lambda. Sorry about this. This is what I'm changing. And because this is not a function, not function of W, like this, like a throwaway. Not a function, so I could throw away. This term, a regularizer. And so ridge regression is when Q is equal to 2. So when Q is equal to 2, then ridge regression. Right? It's the same. So, I'm trying to minimize the residual sum squared and also this regularizer. Okay? I want to minimize this with respect to W. And I'm also maximizing this with respect to lambda. If usually lambda is given. Depending on the problem, you say lambda is 5 or 6. Okay, so just throw this away, and lambda is some constant. So what is this trying to do? Let's ignore this thing for now. Let's ignore this. Let's look at how do I get rid of this? So let's look at this. Let's assume W is equal to W1, W2. Represented by here. It's in a two-dimensional space. I'm going to draw this function in terms of W. Okay. Summation over Wi of this, and I'm going to look at the contour plots. What is a contour plot? I assume that this is equal to some value C. And for different values of C, where are the W's lying? So for different values of C, this would be a circle. So for here is different values of C. It will be circles. Okay, so this, as you go out, bigger C. Bigger C values. Okay? It would make these contour points. Okay. Now I'm also going to draw this. The residual sum squared. What is the residual sum square I had? This is would be y, I, and it would be let's draw it this way for your convenience. That will be the prediction square for, let's say, n data. This is the residual sum, right? Because we're going to take the linear combination of the fees and we're going to take the difference and take the square for all training data. And we're going to look at some contour plots of this. Let's say this is the D. What is this in general, this equation, in terms of W1 and W2? What?
Circle.
Well, not necessarily, so probably a sort of an ellipse. Well, it's probably going to be an ellipse, okay? But I've represented that as circles here, okay? It could be ellipse, but it's circles, okay? So this is the contour plot . This is contour of regularizer. So what is this trying to do? If I'm trying to do this, I'm minimizing. What is that trying to do? I'm trying to minimize this, right? I'm trying to minimize the residual sum squared and also the regularizer. Okay? And I'm going to assume with some ratio lambda. So, what should D and C be? What is the objective of C and D? You want both of them to be very, very small. So this, as you go out here, this is bigger D. Bigger D here, bigger C as you go out. but both of them are trying to be small, right? But you know that the W that satisfies this should be an intersection, right? So there is one contour that's centered at the origin, that's not trying to be big. There's another contour that's trying to be right here. So they're both trying to be small, but they have to intersect. So that intersection is right here. That will be the solution, making both of them very, very small, right? So that's the meaning of this. Yes?
But in this special case, I think that we have W's which will align on one line, like between the center and the center of the second circle. I think all of them.
You can only have one W, right? It's for some W, right?
Okay.
For some W, you want both of these circles to be small, right? One's centered around here at the origin, that's the regularizer. The other one, residual sum is lying somewhere around,
Yeah.
not at zero, right? But these circles, some W will give you some value of C and some value of D.
Yes, and if we sum them and if we try to minimize them, there will be no difference if we make some D, for example, a little bit bigger and C a little bit smaller. There will be no difference, so we will have like a lot of different W's. No?
No, there will be one W that's going to minimize this because it's only one point, right?
Yes.
You know that the more one point is going to be.
But we have like C and D, and we try to minimize sum of C and D. And sum of C and D is the distance between the centers of these two circles. And if we move W like between these 2 points, sum won't change. Am I wrong?
C and D are not the distance. It's like a radiuses, d squared.
Ah,
It's, yeah,
okay, yeah.
okay? So this is the situation in ridge regression, okay? Now let's assume, so this is for Q equals 2. Let's look at the case when Q is equal to 1. When Q is equal to 1, what kind of a contour plot are we going to get?
Lines.
What?
Lines.
Lines. It's going to look like a diamond shape. Whole bunch of diamonds. This is it's a whole bunch of diamonds in this case. And this is the residual sum. Now, you look at this situation and look at this situation. You find that there's something very interesting going on in this situation. So the solution is going to be at the intersection of these two contour plots. Where is the solution here? Huh? Probably at the edge. Most likely. It's very possible that you get it right here also. It's possible. But most likely, with high probability, that it's going to lie right here. So what kind of a W would you get? Yes, the W's. So if it's right here, what is the value of W1? 0. What happens if it intersects at the corners here? What's the value of W2? So, when Q equals 1, you most likely we're going to get a sparse solution. Sparse solution we call that sparse solution. What is sparse solution? If W is high dimension, so it's either going to be 0 W2 or W1 0 or it's going to be in this type of form. So if W is high dimension in general, you're going to get something like this. 0 0 0 0, and then you're going to get some I, and then 0 0 0, which is sparse. This is what we call sparse. Only one of them will be set to 1. Or it's possible that you get 2. But in general, you get sparse solution. These are the different contours that you would get for different values of Q. So this is Q equals 2 was circles, contours were circles. Q equals 4, that looked like that. Q equals 1. Q equals 0.5, looked like that. And for values less than Q, or equal to 1, the contours are going to be what? Are going to be pointy. It's going to be pointy, more pointy like that as you go down. Very at the edges. So, with Q value less than 1, value equal to 1 or less than 1, you're going to get a sparser solution. Okay? Do you understand what I'm saying? So, solving something like this, solving an equation like this, where you're doing residual sum, minimizing the residual sum, and have some regularizer. Let's say I want to write this thing a little bit differently. Residual sum plus lambda regular regularizer, okay. I mean, what is the reason for putting this? What is the reason for putting this, first of all, the regularizer? If you don't have that, what are you gonna get?
Overfitting problem?
You will call that overfitting problem. Hmm? So now just write it. When lambda is equal to 0, you get overfitting. Usually lambda is positive. Lambda is positive. You get so this is what I should say. Larger lambda greater than 0, less overfitting. When lambda is really infinite, what do you get? When lambda is really big, then we get sort of underfitting. Oh? As you get really because this is emphasized, it's not doing the task, right? It's not doing the task. It's just trying to keep it small. When Q is equal to or less than 1, what do you get? You get sparser solution. Sparse solution. Okay? Any questions about this? Yeah.
What happens in terms of bias and variance when we increase lambda? So when we increase lambda, so does the variance increase? Less variance?
So, variance, how would you think of variance? What is variance? We're gonna be talking about that in a little bit more detail, but what is variance? So variance, the way you should think variance is if I change the data, and you're gonna, for each time you change the training data, you're gonna get a different W, right? Is the W going to change very much? That's the idea of variance. We're gonna look at the mathematical terminology. If I change the training data, is my W, each time I find my W, is that going to change a lot? So it's going to depend on the order, the variance, but certainly as you increase lambda, what's going to happen? It's going to just do this and not really look at the training data. So even though you change the training data, it's not going to change very much. So the variance is low. Now what about the bias? I asked, if you know something about the variance, what happens with the bias? he gave an answer, he says, the opposite is going to happen. Huh? And we'll see that they sort of go up and down this way, different. Okay? And we're going to look at that equation because the bias and bias squared times the variance times something is equal to the error that you're going to. Okay, that's the bias variance decomposition rule that we're going to look at. Okay. But people really don't, think about that in a lot of detail. Okay. So here are some interesting examples. Okay. Now, let's look at this. This is an example that was given in the book. I think it was Bishop's book. It's in one of the references. You're given X and you want to predict, here it's T, which is the label, okay, on the basis of this. So the input is n-dimensional and it's a column vector, okay? So there is a corresponding T. But let's assume that T is something like this. So what is it? X is for some value of X, the T is the sine of 2 pi X plus some noise. Okay? And this is in the same form that we were talking about. Y is equal to fx plus epsilon. So, but instead of y, it's t here, and instead of epsilon, we have z here, and we are going to assume that x is within, in the range between 0 and 1. Okay? So it's one period. But let's assume that we don't know this. Okay? So we have training data where we have just X and T. We don't know this. Okay? And let's assume that we're going to have our loss function as the residual sum, or the mean square sum. So here is the t value that we're trying to predict. Let's say y is our prediction. Okay, this is the notation that they use. So sorry about the confusion. Tn is the value of that for some xn value, and my prediction is going to be, it's going to be based on x of n, and it's going to use the parameter w. W to make my prediction for Tn. And my loss, my criterion, is the difference squared for all training data. How many training data? N. And I put a half here, or where the book puts a half in there. Why do you think you put a half here? If I take the derivative, then the 2 comes here and then multiplies by half of that for simplicity. Okay? So what is my model for predicting that? And here in this case, what was my model here? It's a polynomial. Okay? And what's the polynomial? Nth order polynomial. Hmm? So what is, if we're going to linear basis function, I define what a linear basis function is. In regression, we try to, our y is going to look, oops. Y, if I write it in this, it's going to look like this. That's my linear basis function, right? Hmm? So or I could just write it this way. Okay? This was our linear basis function, remember? So what are the phi's in this case? What is phi I? So this is linear, right? It's linear. What are phi i's? It's, huh? X to the power I. Hmm? That's the basis function. But it's a linear basis function, right? And I want to find my W that minimizes this. But, so you see the situation. I'm predicting the sign with what? With a polynomial. This is the scenario that we have. And there are some knowns. This is probably in all real world problems. This is the situation. I don't know what that f of x is going to be. This is f of x. Remember I had y is equal to f of x. Deterministic. And this was stochastic. Remember this? And I went through, tried to describe this model. So, this is a situation, and people have worked out some examples. So the green represents the sine function. The circles represent data. Why aren't the blue ones lying on the green?
Plus Z.
Pardon?
Did it plus Z?
Plus?
Z.
Oh?
Z.
Oh,
Z.
sorry, yes. The noise. The noise. Okay? And I said why these noise would be. It's maybe measurement noise. It's just noise that's coming. So this is the data. And I'm going to use a zeroth order polynomial. What is a zeroth order polynomial? It's just a constant. Okay. So here is a line. Okay. It's m equals for m equals 1. M equals 0. Oh, I'm not satisfied with the E, the error. What is the error? So this is training error. I could figure out what the E is. How would I do it? I'll take the square distance, squared, 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 and I'll sum them up. Okay? And then I had a half there, so I put a half. Okay? I'm not satisfied with that. So what do? I increase the order. Then I have a linear line. And then I also do this. I'm not satisfied. I do it for m equals 3. And I do that. Okay? So what the error is seems to be getting better. The error seems to be reducing. Then I go to m equals 9. What is this? The error is what?
0.
The training error is 0. But is this a good fit? No. I have, this is good. You can see the training error is 0. Why? Because I have 9 data points. Was it 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 data points. I have a 9th order. How many coefficients do I have? 10. So 10 variables, 10 coefficients. I could get them perfectly. But you can see that it's going crazy in other points. Is this going to have good generalization? No. So, you talked about bias and variance. You can go through this case as you increase the order. Let's talk about that. Let's talk about the bias and variance. Okay? What is the definition of bias?
How our results depend on the model that we have.
So bias sort of represents, this is a little bit of high, represents the flexibility of the prediction, flexibility to follow the data, okay? Or it's sort of the average value of, as you train the training data, the average value that you would get. Okay. So, as you change the data, what's going to happen with this? Is this high bias, or as you go here, high bias or lower bias as you go here? From here to there. Low bias. Low bias as you're going from here. Okay? And as he said, If you have going to low bias, what's going to happen? You're going to get high variance. What does high variance mean? If you change the data, your result will be different all the time. And this one will be, depending on what the data point is, going to be crazy. Huh? This is the plot of the training error. This is the plot of the test error. And you can see that the training error went down as you went through ninth order. The test errors, what is a test error? So you just generate another set of data not used for getting the coefficients. Huh? Data not used to get the coefficients. And you see that at ninth order, it just jumps up. We would expect that. So how do we, if we look at the solution, can we sort of see from the coefficients, oh, we have overfitting. Both of them high, so this is underfitting. By looking at the coefficients, how do we know we have this kind of a situation? How do we know this?
We can check when trading, we can check time by time. If it goes up, we can stop trading.
Which goes up?
And if testing error goes up for consecutive runs,
But testing error in reality, we don't know the label.
we can see
Oh.
cross-validation.
What?
Cross-validation data.
Cross-validation.
Check
Yes.
on that. And if it goes high, then we can stop and check the data.
So you need to check. You need to check. Okay, as you increase the capacity. But there is something. Yes.
The form of says conditions is equal to number of data. It means that
I want to just say something else to you. How do you know it's overfitting? This is what I'm going to say. Look at the coefficients. M equals 0, 0.19. These are the W's. From the coefficients, can we sort of see overfitting? What is this doing? Sometimes it's very difficult, but if you have W that's going crazy, minus plus, it's going crazy. Why is it going crazy? It's trying to, what?
Fit every point.
It's trying to fit every point. It's trying to fit all the training data, and it's going crazy, W's. So, when your coefficients go crazy on you, you probably know that it's going overfitting, because it's trying very, very hard. So how do we do this? Well, how do we stop this. Hmm? So what was this? How do I get this solution? How do I get this W's? Minimizing the residual sum, or half the residual sum, the sum squared, right? But what do we actually put regularizer. What does regularizer do? Hey, in addition to the residual sum squared, I say, hey, I'm also thinking about the sum square values of the coefficients. I want you to minimize the residual sum square and also minimize the how big the W's are. Then it's going to sort of prevent that from that happening. Okay? So that's no, but also let's look at this. Hey, what's happening here? Ninth order. We have ninth order. Hey, ninth order is going to lead to overfitting. But for ninth order, hey, it's doing a pretty good job here. Wow. Ninth order is good. You just said that ninth order is overfitting. So what's the lesson to be learned here? This is a situation with how many data? 15. This is 100. So, overfitting. What can you say from this? It depends on how much data you have. Huh? If you have infinite number of training data, then probably no overfitting. No overfitting. But we don't have infinite number of data. We always have finite number of data. So, if you have finite number of data, that puts a limit on what we can learn. So, don't be greedy. You're given 9, 10 training data, and I want to perform as if I had 100. That would be dumb. That's not. It doesn't happen that way. You're given 10 data, and there is just fixed amount of information, and you cannot do ninth order. Purely. Okay. So the thing is, overfitting depends on how much training data you have. That's a very important lesson to it. Okay? This is, everything, I see that students send me some project algorithms with deep learning and went to quite a detail about deep learning. I didn't teach deep learning yet. Wow, and I said, Jesus, how does these students, I was just amazed. Well, one guy proposed, I'm sorry about this, I'm not trying to make fun of you because, some students are way ahead of me. Tracking. Let's do tracking. Wow, I was just amazed. But, in deep learning, whatever, these fundamental rules of machine learning is applicable. Okay? It's not you have a set of rules for deep learning, set of rules for this. This is for all machine learning. Okay, by the way, Q equals 1, we call this, when, here, when Q is equal to, it's got a name. Q equals 1, it's called lasso. It's called lasso. And I don't know, it's an acronym, I mean, for something, and I don't remember. It's lasso. Lasso is very easy name. Lasso and ridge regression are some of things like this. Yes?
So there has been like the problem of deep weights,
What?
like problem of deep weights. Large
Problem of equate, what is that?
No, like large weights. When you have
Huh?
large weights, so it's all easy to say.
Problem?
Like you said, if weights become large, so it means overheating.
So yeah.
So what if you just bound weights?
Yes, that's what we,
Oh, like you just say like if it's bigger than some value, it should be like this round.
that's the same as minimizing the sum squared or the sum q's. It's the same thing as you bound it. You want the sum of the weight to be bounded by 5 or 6. That's the same as minimizing that weighted sum squared, or of all the regularizers that we. Okay. In fact, this I was just going to skip that.
It's also professor.
So you're talking about. Let me just answer your question to this one. So here, minimize this. Well, minimize this, and I want this to be bounded. Doing this is the same as that.
And also,
Oh,
what if you just normalize weights every time?
normalize the weights. Normalize the weights. Normalize the.
Is it around 0 instead of bound by 1?
Yeah, normalize the weights. I think. Still, normalizing the weights. Normalizing the weights is, but you have to have a high bias, a W0 value. Because if, I mean, normalizing the weights, one of the term has to be large, or you have to scale it. You have to scale the thing at the end, right? That scale value will be huge. Well, anyhow, even though you normalize it,
And just if you linear scale it.
yeah,
Okay.
it doesn't work. I don't think it works. Okay. Okay, I want to just go to this right away. So now here, let's look at this. Instead of the EW that we looked at, which was just this, I put this in here. Or the example, the book put this. Okay? And look, in this case, I have 9 training data. 10 training data. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 training data. And I use a 9th order polynomial. Okay? When I did that, it was crazy. The training data, right? 9th order polynomial with training data, it was going back and crazy. Okay? Now, here, lambda was set to, log of lambda was set to minus 18. So what is that? Lambda is e to the minus 18. Is that a large number?
No.
That's a very small number. Huh? Very small number put here. What happens? And that's regularizer. What happens? Oh, it behaves nicely. But what happens if I do this? Log of lambda equals 0. So what is lambda? E to the 0 is 1. So compared to that, 1 doesn't seem like a large number. Well, it doesn't seem like a large number, but what happens here? What is the situation? This is a ninth order polynomial. What happens? It's not moving at all. This is taking over. And what kind of a situation do we have? It's like underfitting. So just a little bit of regularizer can help you. But if you go too far, it doesn't seem like a lot. Lambda is equal to 1, you get that. And these are the coefficients. I'm sorry about this. These are the coefficients when, what is this? What is lambda here in this case? 0. You get crazy. This is reasonable. Small number. This is lambda equal 1. You see that? What happens? The coefficients. It's just all zeros. Okay, this is about all I need to say, and as you see, as you increase the regularizer, what happens? What's here? As you have small lambda, really, really small. What's here? What do we call this? This is training, this is test. Sorry about this. Training and test error. What happens? What do we call here? No, we call this, I want to say, overfitting. What is overfitting? The training and testing are big difference. What about here? Underfitting, right? And bias, right? Understanding all these terminologies, that is underfitting, and then you have high bias. Okay, I stop right here. Okay, and I'm going to assume that I've finished regular regression. So next time I do bias, and today.